Welcome, everyone. Today we're diving into a critical topic for building scalable, cost-efficient systems: intelligent log batching. In the world of high-traffic applications, every network call carries a hidden cost, and understanding how to minimize this is key to performance and infrastructure savings. By the end of this lesson, you'll gain practical insights and be equipped to implement these strategies in your own projects. Specifically, you will be able to, first, understand why network overhead is a critical bottleneck in modern systems. Second, you'll learn to implement core batching patterns like dual trigger and bounded queues, which are fundamental to efficient data handling. Third, we'll cover how to design your systems for graceful degradation and ensure data durability even when facing high loads or unexpected failures. And finally, you'll understand how to optimize batch payloads for maximum efficiency and apply these real-world strategies used by leading tech companies. Let's get started. Let's first understand the core problem. The network is your bottleneck. Every single log transmission, no matter how small, incurs significant overhead. Think about it. TCP handshakes, TLS negotiations, HTTP headers, and even kernel context switches. At scale, this overhead isn't just a minor cost, it dominates your infrastructure expenses. Imagine Netflix processing over 500 billion events daily. Sending each individually would be astronomically expensive and inefficient. This is where batching comes in. We accumulate data points and wait for a trigger before transmitting in bulk. The fundamental challenge is balancing latency and throughput. Production systems solve this with dual trigger batching, flushing when either a batch size or a time interval is reached, whichever comes first. For example, sending 1,000 logs or waiting 5 seconds. This ensures you get high throughput during peak traffic and bounded latency during quieter periods. Another critical pattern is using bounded queues. Without them, an overwhelmed producer can lead to unbounded memory growth, eventually causing your system to crash due to out-of-memory errors. Bounded queues apply back pressure, preventing this memory leak by either blocking new logs or dropping them when full, depending on your strategy. While batching boosts efficiency, it also introduces complexities around resiliency and data durability. What happens when your system is under extreme load? You need a strategy for graceful degradation. This means deciding what to prioritize, maintaining low latency by dropping some data, or ensuring durability by accepting higher latency. For example, application logs might be droppable, but billing events never are. You can implement adaptive batching. Under normal load, use standard parameters. But if your queue depth exceeds, say, 80%, start sampling or even dropping non-critical logs entirely. Crucially, always preserve error logs and transactions. Another major concern is at least once delivery semantics. Batched logs are temporarily held in memory. If your logshipper crashes before flushing, those logs are lost. To mitigate this, flush batches frequently, every 5 seconds maximum, even if partially full. On shutdown signals, flush immediately. For truly critical logs, consider a write-ahead log pattern. Persist to local disk before batching, then mark as committed after successful transmission. This balances the efficiency of batching with essential durability guarantees. Beyond just batching, we need to think about the payloads themselves for maximum network efficiency. Not all batches are created equal. A batch of 1,000 small logs behaves differently than 1,000 large logs. Network efficiency depends heavily on the payload size relative to the fixed overhead. Small payloads waste bandwidth on headers, while excessively large payloads risk timeouts. The sweet spot? Aim for 100 kilobytes to 1 megabyte batch payloads, regardless of the record count. This maximizes payload density and significantly reduces the overhead percentage. For example, a 100-byte log with 500 bytes of overhead is 83% waste. Batch 1,000 such logs, and you get a 100 kilobyte payload plus 500 bytes of overhead, hitting 99.5% efficiency. That's a 200x improvement in network utilization. This principle is why major tech companies aggressively batch. AWS Kinesis, for instance, automatically batches with 500 kilobytes or 1-second triggers in their SDK, transparently reducing their customers' infrastructure costs by a massive 90%. Uber batches trip events with 5-second windows before feeding their machine learning pipelines, reducing their Kafka cluster size dramatically while maintaining sub-10-second data freshness. These are not just theoretical gains, they are real-world, measurable improvements. We've covered a lot today, and I hope you feel empowered to tackle network optimization in your systems. Let's quickly recap our key takeaways. First, remember that network overhead is a major cost factor in distributed systems, and ignoring it leads to significant inefficiencies. Second, designing an intelligent batching system is all about balancing throughput, latency, and data durability based on your specific use case and SLAs. Third, implementing bounded buffers and adaptive batching strategies are absolutely crucial for maintaining system stability and preventing cascading failures under load. By applying these principles, you can achieve remarkable improvements in network utilization, reduce infrastructure costs, and build more resilient applications. As a final thought and a self-assessment for you, how would you approach designing a batching system for critical financial transactions differently than for application logs? Think about the trade-offs and strategies we discussed.